Hey everybody, thanks for coming to our final, super final last workshop, last day, last afternoon session. So the first of our last two talks is Emma Brunskill, who unfortunately will have to make this the RL day all by herself. Sorry that you missed the Tuesday RL day.
Thanks everybody for coming out. Earlier this week I was giving a mathematics of machine learning summer school up at University of Washington, and I think it's a really exciting time to be doing reinforcement learning. I was just saying to Peter, I think it was amazing to see that there was about 150 people at the theoretical RL session of ICML, which definitely did not used to be the case. So maybe I could just do a quick show of hands. Who was here on Tuesday when there was a wonderful plethora of RL talks? Okay, so a number of you are probably RL enthusiasts, but I find it always really motivating to think about the past and where we're coming from. And it's a pretty lovely quote from Stuart Russell, who is Stuart Russell and Peter Norvig's book, where they talk about Aristotle being one of the first people to talk specifically about sequential decision-making under uncertainty. And the idea of a doctor reasoning about the final state they want to get to the patient, and then doing sort of eventually sort of backwards chaining from that final desired state towards the series of actions that need to be done. And now we might call that something like dynamic programming. And in fact, about 2,000 years after this sort of vision was realized by Newell and Simon, who are two amazing researchers at CMU. So I think it's incredible to think about how long we've been struggling with the issue of how to make decisions under uncertainty. And of course, in many cases, we're learning to do this. We don't have a model of the world. We're unsure about how to do this. And this is something that kids start to do from the very beginning. But I think that we only really started to see this formalized in kind of the 1940s. 1930s to 1940s is the first time people started to think about multi-armed bandits and reinforcement learning. And I really think that sort of it was only in the 1980s that we started to think about reinforcement learning in the way that the field thinks of it right now. Though, of course, there's been a lot of amazing work in the controls community. But as we've entered the last decade, I think it's really a completely new era of reinforcement learning. And probably everybody here is familiar with these types of results that are really outstanding. And maybe not for anybody in this room, but certainly when I talk to some of my colleagues, even just further away in other aspects of computer science, and certainly when I talk to my colleagues that are not computer scientists, and I tell them that I'm doing reinforcement learning, they have some questions. So they might have heard of the Go result, and I love this visualization from DeepMind of thinking about the incredible branching factor of the decisions that are being made with Go. But people that have heard about this result naturally say, if we can do this, if we can do something that was such an enormous intellectual feat and wasn't proposed to be finished for at least another 10 years, well, what are you doing? Is reinforcement learning solved, and how are you continue to publish papers? And when I think about the work that we're doing in my lab and many other labs, I think about the parallel legacy of reinforcement learning to try to benefit people. And so really from the very beginning of when people started thinking about artificial intelligence and reinforcement learning, they started to think about how could it be used to augment people in addition to how could we achieve human level or replacement people capabilities. And in a lot of my work, I think about the technical challenges that come up when we think about specifically systems that are going to interact with people and augment people. So if we think about Go, or if we think about robotics, we typically think of there being a simulator of the domain, having access to enormous amounts of data to train with, and that we can always try out a new strategy without a lot of harm. So that as long as we eventually learn a really good Go player, then that's sufficient. But in the context of people, so far we don't have good simulators of human physiology, of behavior, or learning, and gathering real data involves impacting real people. And so that introduces sort of the main focus of what I think about with my students and with my lab, which is how do we think about techniques to minimize and understand what data is needed to learn to make good decisions. And I think this is not only sort of a foundational quest within reinforcement learning, but I also think that it has this key implication, which is if we can learn to make decisions faster, if we can need less data, then more people can benefit. Because if I think about sort of making something like a tutoring system, if my tutoring system needs 8 billion data points to learn, well, then there's nobody left to benefit from my amazing tutoring system. So what I'm going to do today is talk mostly about a question I've been really excited about for the last 5 years, which is counterfactual or batch reinforcement learning. And then if there's time, I'll go to the end. But I sort of switched the order of this because I want to make sure to get to this to start with. So this is probably going to be familiar to everybody, but just in terms of notation, in case there's only control theorists, I'll make sure to say that I'm going to use S for state. We're going to have a decision policy, which is a mapping from states to actions. We'll take actions in the environment. We'll see rewards. And we'll think of there being value functions, which are the sum of immediate rewards plus discounted sum of future rewards. And we're going to care about finding the optimal value function. And we're going to be interested in the reinforcement learning setting where we only observe this through samples or experience. And in particular, I'm going to be really interested, at least in the most of the talk today, when we don't actually get to gather this experience. And my interest to this comes from when I was collaborating with Zoran Popovic around 5 years ago. So we were starting to collaborate together with some students, and this is the game Refraction, which teaches students about fractions. And so the idea in this case is that the students have access to different laser beam splitters that they can use to fuel a spaceship up here. This game has been played by somewhere between 100 to 500,000 people. And what we wanted to figure out is how to help people persist. This is an optional learning activity. People can log on to this. They can go over to Facebook or YouTube whenever they get bored. And so this has a high barrier in terms of potentially losing people. And we wanted to think about decision strategies to try to keep people engaged. This is where the reinforcement learning part comes in. So we want to think about sort of conditioned on the past levels that they were doing and their performance, which could be as simple as something like how long they took to complete the previous level. What is the next level I give them in order to keep them engaged? So my reward function here is going to be how long they continue, how many activities they do in this game. And my state can be anything. My state could be something really simple like this, or it could be the complete history of prior activities they've done. It could be where they're clicking on the game. It could be all sorts of other features of the environment. And what we didn't want to do in this case is we didn't want to do random exploration. Because this was an optional game, people talked about it. If we were doing things that were completely frustrating to lots of people, nobody would ever play this game again. But what we did have access to was a limited data pool of about 11,000 learners' trajectories with random actions. So essentially, they got random series of activities through here, and then we looked at how long they persisted for. And so the goal in this case was to learn a new policy that we thought would help people persist for longer. And this was the first time, I'd been doing reinforcement learning for a while before this, but this was the first time I really thought about this issue of sort of counterfactual or batch off policy reinforcement learning. Before this, I'd been thinking a lot about exploration. And this is the case now where we have a data set of n trajectories, which are gathered from a behavior policy. Now, for most of this talk, I'm going to assume that we know what this is. In practice, we do not always know what this is. I'm being very interested in observational healthcare records right now, and we don't know what that is for physicians. They don't tell us with probability 0.9, I prescribe Tylenol, and probability 0.2, I do aspirin. They don't give us that information. But in the context of many robotics problems and in our fractions problems, we knew this. In this case, this was uniform. And so the question in this setting is, how do we use this data to make better decisions? And people are sometimes also calling this sort of what-if reasoning. So if we think about there being a series of decisions that are made for an individual and seeing some sort of outcome variable at the end of this, then the question is, as a new individual comes in, what should we do to maximize their outcomes? And this is a hard problem because data is censored. So just like in the multi-arm bandit setting, which I know multiple people here work on, we can't tell what would have happened if we took a different series of decisions. So if right now, if you had decided to instead go get coffee at one of the many fine establishments nearby, you never know how wonderful your life would have been under that particular trajectory. So we can't see what would have happened for the same individual if we had done a different series of treatments. So that's the first challenge, and that comes up even in the case of multi-arm bandits. But I think the second really big challenge in this case is generalization. In that even if we just have a discrete set of actions, if we're making a series of choices, then the number of possible combinations of action sequences is going to grow exponentially. And it's just not going to be possible to try all of those. So historically, the way we normally deal with figuring out what's the right thing to do for high-stakes scenarios, like clinical trials, is we do a randomized control trial, and then we just explore all the conditions. But the problem is that's not going to scale very well as we start to have lots of sequences of interactions. And we think that in some cases, the sequences of interactions might be really important for deciding what's the right thing to do next. So I think it's been really exciting to see that over the last year or two, there's a lot of excitement and growing interest in the intersection between causal inference and machine learning. There's been a huge, amazing literature tradition in causal reasoning for a long time. And now we're starting to see a lot of people in machine learning thinking about this, particularly, and including in the deep learning communities, because people want to think about building models that are going to generalize in some strong way. So in particular, the problem that I'm thinking about, and started thinking about motivated by this fractions problem, is batch counterfactual policy optimization. Meaning that we want to pick a decision policy that when we deploy it in the future is going to do well. And so one way we could maybe formalize this is to think about us estimating the value of a policy given an input data set. And we might want to be making some sort of model selection over a policy and given some different hypothesis classes. I think this is already, there's some interesting differences compared to supervised learning because the hypothesis classes we pick could be models like reward models and dynamics models of the environment. They could be value function classes, or they could be policies. So there's already some different choices of what do we even mean by the hypothesis space here. And then there's an additional challenge, which is this question here is often referred to as simply policy evaluation, which is someone gives you a policy and then you want to know how good it is. And there's been a lot of focus on this, including by me and my students. But a couple years ago, we noticed that that's not sufficient, which other people have also observed. And the challenge is that even if you get an unbiased estimator here, which we often try to get, then that can fail in terms of some notion of fairness. Now, fairness here, I don't mean in the sort of fairness, accountability, transparency movement. I mean in terms of us picking a policy that has higher value at least 50% of the time if it's actually better. And intuitively, the reason for this is just because of the bias variance trade-off. So by getting an unbiased value estimator, you are going to have zero bias, but some of your policies might have very different variances than others. And so you can systematically make wrong decisions. So that made us increasingly interested in whether or not we could kind of more directly think about the policy optimization question. And I would argue what we've been trying to do over the last couple of years, and there's still a huge amount to do, is to really try to do something like structural risk minimization for decision making. So often, again, when I talk to colleagues of mine that are not in reinforcement learning, I explain doing this problem, they say, well, that's solved. We have cross-validation, we have structural risk minimization, why don't you just divide your data into a train and test set, build some policy, evaluate it, and then you're done. The problem is that those types of approaches require us to do some sort of evaluation and often have some sort of generalization guarantee. Normally that's maybe some function of like our hypothesis class flexibility. And I just don't think we have that yet. I mean, certainly there's been a number of us that have been thinking about this problem, but I don't really think we're there yet. And I think that it's a really exciting opportunity for us to try to get there. And I'll say a little bit about some of the steps we've been doing to try to get towards that. So in particular, we can think of this as sort of being a split between policy optimization, policy evaluation, and getting error bounds. Ultimately, we might not want those. We'd still just want some sort of useful procedure like cross-validation, but I don't think we have that either. Many of you might be familiar with this part, but I just want to highlight why this problem is so hard, even without the bound aspect. And I really like this recent figure from a Nature medicine paper from David Sontag, Finale Joshi Velez, and some of their groups. And the challenge is that in general, for different decision policies, we're going to take, by definition, different decisions. But the problem is that those different decisions affect not just the immediate reward, but they affect the next state you get into. So if we think about something like a healthcare application, let's say this is actually our data set. And then under our policy, for some threshold, we would actually do mechanical ventilation for everybody who has that particular symptom. Well, for a whole bunch of people in the original data set, the doctors didn't do that. So now we reduce a lot of the number of people that we have. And then let's say if those people experience discomfort, then our policy would prescribe some amount of sedation. And so now we have an even smaller cohort. And in general, the amount of data that matches a particular policy we might want to evaluate is going to shrink and shrink and shrink. It can shrink even exponentially with the number of decisions that are made. And so that means that often the amount of data that we have to try to do this optimization or try to compare across different policies is very small. And so the noise can be very, very large. So I think that the big challenge right now is that there has been quite a lot of progress on policy evaluation, but trying to combine this with policy optimization and error bounds, I think there's still a long ways to go. And I'll highlight why. So I think some work kind of that leverages things like importance sampling bounds, provides unbiased estimators, but it typically ignores anything about whether you've got a structured policy class, and it relies on things like Hofting and other concentration inequalities, which typically require an enormous amount of data if you have high variance estimators. So if you have sort of web scale data, I think this can work well. My former postdoc, Phil Thomas, had done work with Adobe, and they could apply these type of bounds there. But for other cases, like for mobile health, some of their initial studies is like, maybe 200 people. We're just not going to have enough data for that setting. A second case is to make sure that we use some sort of kernel function or averager approach. But those typically need number of samples that is exponential in the input state dimension, which isn't going to allow us to capture the really rich types of features that we now have access to. A really important line of work is on fitted Q iteration, and I think Nan spoke earlier this week. I haven't seen his talk yet, so I don't know if he talked about this particular line of work. Nan Zhang had a nice recent paper in ICML, as well as Yisung Yu's group, where they're providing new fitted Q iteration bounds. Fitted Q iteration is going to use a function approximation estimate for this. The problem is that often we require realizability. We require our function class to actually include our true value function, and that's often not going to be the case. And if you don't have that, then we normally end up with a bound on kind of the inherent Bellman error. And the problem with that is that that's going to depend on the MDP we're in. We don't know which MDP we're in, and so they're not generally going to be evaluatable. And the problem with it not being evaluatable is that then there's some challenges for model selection. I think that Li Hong Li was also here earlier this week, and he might have talked about some of the new primal dual approaches, for trying to do value function estimation and optimization. I think those are also really promising, particularly from the practical side, but they tend to have similar dependencies. So I don't think any of these methods have really given us a satisfying answer for, can we have some sort of error bound here that depends on sort of how complex we're assuming the environment should be, so that just like in supervised learning, we can make some assumptions of how good a linear regression would be, regardless of whether we need to assume that the world is really satisfying linear regression. So this is our goal. What we would really like to do is to sort of have these nice, strong generalization guarantees on a policy performance. I think that's really hard. We're going to move the goalpost. So the goalpost instead is going to be, what if we could just guarantee we find a good in the class policy? That's a much weaker assumption. That's just saying, given some policy class you have, can you do pretty well? But maybe that's going to be a little bit easier, and then I'll get to a stronger guarantee shortly. So this is joint work with Alec Agarwal, led by Yalu, my student, also Adis Horman. And the idea in this case is for policy gradient methods, we're going to define a policy class. And we want to try to find the best policy in that policy class, but we want to do it in the offline setting. So one thing, I think policy gradient methods are incredibly powerful. One thing that I find less satisfying about them is that often you just throw away your previous data and you gather more data when you next run it. And up till now, most of the time leveraging the prior data hasn't been all that helpful. And one of the limitations is that when you gather more data from the new policy, then you want to be able to incorporate the fact that the distribution of states and actions you observe is different depending on the policy you have. But there's been some really nice recent work from sort of 3 separate different groups Shai Manor and his students, and Li-Hong Li and his collaborators, and also Mark Bellemere and some of his students have recently all developed methods which work on the stationary distribution of the Markov chain. And this is really nice because instead of having sort of thinking about things at the trajectory level, we're thinking about things in terms of the stationary distribution over states and actions that we might visit under the state, and ratios of how much that changes under our behavior policy versus a target policy. And so what we observed is that we could use that, most of that's been done for policy evaluation, but we could use that within a policy gradient approach in order to get much stronger results. So now we can change like sort of the policy gradient algorithm to incorporate this new ratio. And that gives us some nice convergence guarantees, but perhaps more importantly, it gives us some really nice insights for using old data. So this is cart polls, one of the classic simple examples. And what you can see in the red here is the behavior policy. So the behavior policy is not very good. It doesn't get very high reward, but it gives us enough information that we can use it to learn a much better policy. So here we're comparing most of the previous methods for leveraging off policy data. Either assume you get access to additional data or don't try to correct for sort of the state action distribution mismatch. And what you can see here is that our method up here does much better than those. So this is just policy gradient steps, but this is policy gradient steps all with the same data. So we're just given a batch set of data and we're going to do a bunch of gradient steps on that data. And the really cool thing to me is that you can see that even though the data, the performance of the policy that you have access to is not very good, you can actually learn a policy that's basically near optimal using that data. So why is that important? Well, you could imagine embedding this. In fact, Alec and I and Yao were just talking about embedding this within an online learning algorithm. And this just means that hopefully we can squeeze a lot more information out of our data and we can take bigger jumps. So instead of taking lots of small steps to try to go from here to here, where we're actually running this in the real environment, we could just take this data from the real environment and already jump up to here. And so that would be awesome because then we would need way less data to get to the same level of performance. Okay, so this is exciting, but what this is doing is trying to converge to sort of a local optima, doing policy search. This still isn't getting at sort of the stronger guarantees that I said we wanted to try to get to. So let's think about if we can make it a little bit closer to what we want. So maybe instead of saying we're still going to do sort of a restricted search, but now we're actually going to try to guarantee we find the best in the class policy. So not just a good policy in our class. And so maybe we'd want to be able to do something like the following, where we have a best policy in our class, and then we have the policy that we select, and we want to have some sort of regret bounds. So what we want to say is we have more and more data, depending on how complicated your policy class is, then we're going to get better and better at our ability to select a good policy with some sort of, good rate in terms of how much data we have. So this is going to be a global guarantee within our policy class instead of a local one. And so this is some work that I've had the opportunity to do with Xingqun Ni and Stefan Wager over at Stanford. And we basically have this sort of result now for a particular type of policy learning. And in particular, the type of policy learning we're doing in this case is when to treat policies. So as an example of this, you could imagine something like HIV, and you're not going to start treatment until CD4 count, a measure of sickness, is going to drop below a certain threshold. And at that point, you're going to start the treatment. It's a little bit like optimal stopping problems, except for in addition, when you stop, you're going to get to decide amongst one of a set of actions. So like, I have some threshold for when to start treating, and when I treat, I get to decide amongst a set of things. Or like some decision on when I retire. When I retire, I get to pick amongst a set of different, retirement packages. So it can be used to represent things like this. Or another form of kind of a linear threshold policy would look something like this. Maybe you have a function of time and some health metric, and you're either going to turn the treatment on or off at a certain point. Yeah.
This DH covering number you had on the previous slide, was that based on the trajectory you followed, or?
Great question. So we are going to need covering in terms of if your data doesn't cover, you're only going to be with respect to if you can find an optimal policy with your data. So like for example, maybe the optimal thing for some people is to do treatment 5. If you don't ever try treatment 5 for those people, you won't be able to find it.
But otherwise, that was a regular, I mean, it was a lot of covering over, and do you mind showing it again?
Sure.
Okay, so it's like what we expect, except this DH is something about the different policies. Or
Yeah, you would expect it to be. So one thing to be clear about here too is, so if one general challenge is you're making a sequences of decisions. If your behavior policy is really different than the optimal policy, then your coverage can have very little data that matches. And so we're going to suffer from that here too. So you're going to need to have sort of sufficient coverage. You're going to need that some of the time you actually did the optimal thing, and you're going to depend on that in terms of sort of the rates. Okay. So the key question is, how do we do this? What is the algorithm? How do we construct that optimal policy? And this has been an area that's been new to me, that's been really exciting to start learning about. So the first thing we do is something that's quite common in reinforcement learning, and it's also used in deep reinforcement learning, which is an advantage decomposition. So in our case, we're thinking about the difference in the expected value of following a policy pi versus never acting, because we're doing when to stop and treat, and so we're going to compare this to never acting, so it's the delta between the value of those two things. And both Sham Kakade and Susan Murphy have both thought about this particular advantage decomposition, where we think about what is the distribution of the states that you would reach and compare the difference in the expected value if you start treating now versus on the next time step. So we have these two differences here. And the nice thing about this is that this looks sort of like a bandit problem. So it's just, do I treat now or do I treat at the next time step for a fixed thing that you would do on the next time step? And we're going to end up doing sort of estimating just this quantity with a doubly robust estimator. So we can try to use doubly robust estimators from statistics to try to get a good estimate of this. And the interesting thing to me has been about learning about this area of sort of semi-parametric statistics, which I'm only starting to learn about, where we treat some of these things that we need to estimate as nuisance parameters. What we really care about is this, so that we can pick pi star with a max delta. But what we're often going to end up doing is estimate value functions so that we can get at that policy. And we're going to end up treating those as well as the probability, like our behavior policy, which we might not have direct access to, as nuisance parameters that we can use to try to get at these quantities we really care about. And the reason that I'm really excited about this, in addition to, of course, it being beautiful math, is that in a lot of the problems that I think about, we have an enormous amount of noise. One of my students right now is interning at a healthcare company, and in many of these scenarios, compared to sort of some of the beautiful signals we sometimes see in Atari, it's really hard to see what is the effect that the action is having on the state and the resulting reward. And so I'm getting increasingly interested in how can we try to find methods that can extract what is the signal that we get from the actions themselves over and above perhaps very complicated stochastic processes that are determining the other aspects of the reward function. So when we use this, we looked at a couple different sort of health-inspired simulations. And we thought about the case where you don't actually know the behavior policy, that you could estimate it. I also think that's a really interesting technical question, which is whether or not you have compounding, or whether or not you can trust that you have all the state variables you need to understand the behavior policy. In this case, we're assuming we have those variables, but we don't know what the behavior policy is, so we're estimating it. And then we wanted to look at linear decision rules here. And what you can see is the graph didn't come up. The lights are a little weird, but this is essentially the amount of data we have, and this is regret. So comparison of what's the policy we output compared to what's the optimal policy that's possible in our function class. And fitted Q iteration is a really popular method. It's sort of an analog to what's being done in DQN. And you can see that it doesn't do so well. And the intuition for that is that it's going to have low variance but high bias, because it's a particular parametric representation. If it's not flexible enough, it won't be able to capture an optimal policy. So even as you get more data, it's not going to continue to get better. Whereas our method continues to improve as we get more data, similar to an importance sampling method, but it can do it much faster. And we can see these also in sort of a second domain, which has similar properties. But I think even more importantly than this, it can be much more interpretable. So I collaborate with Finale Joshi Velez's group a lot as well, and we trying to think about how we could make the output of these sorts of algorithms useful to doctors. And one of the things we think about is how we would present information about why we're making different decision recommendations. So our method, because by definition we're constraining the policy class to be simple, so in this case it doesn't have to be a linear threshold policy, but here it is. This is the learn linear threshold policy. We'd say, keep the treatment on until you cross this threshold and then turn it off. And so that seems like something that doctors could look at and then argue about whether or not that's reasonable or give us feedback of whether we've specified a reward function correctly. But fitted Q iteration would do something like this, because it's not constraining the policy to have any particular structure. And so that means you get these weird blips where it's like, okay, well, from right here, I should suddenly change my decision, and then I change it back. Or here, and it's not very smooth. And it seems like it's a little bit brittle. And so if I was looking at this as a doctor, I'd sort of say, well, why does it suddenly make a slightly different decision there? Is that due to the fact you don't have enough data? Or is that really that there's some sort of complicated function there where it's much better for this person, this particular stage to do better? I think that's one of the reasons also that it's, not only is it more tractable to start thinking about policy class estimation, but also where it can be beneficial because it's an easy place for us to impose structure that might be interpretable to others. So in general, we've been doing a lot of work on this spectrum. Bless you. I think that there's a lot of really exciting things to be done on the context of sort of policy optimization, policy evaluation, and error bounds. And we're also thinking about this for some other perspectives too, of how do we get error bounds that allow us to have guarantees on things before we deploy them to try to provide more safe AI as well as trustworthy AI. But I also just want to highlight that there's a lot of other really exciting work that's being done by a lot of my colleagues, both in sort of the theoretical front as well as thinking about these for practical cases where we could deploy this. But I think we're only at the very beginning. I think it's really exciting to see the number of people that are starting to talk about counterfactual RL. There was a tutorial at UAI a few weeks ago. Suchi Saria, who does a lot of really amazing healthcare work, is thinking about this. And I think one of the big challenges too is that almost all of the theoretical results require quite strong assumptions, including no confounding and including no intersection. No intersection meaning that the decisions we make for one patient don't affect another patient. That's probably true there. If we're using this to, say, provide incentives to Uber drivers, that's probably not true because Uber drivers talk to each other. And so there's a lot of really interesting technical challenges that come up when we want to think about these for real systems. I've sort of sketched out a lot of the hard things about doing this and why I think we still have a long way to go. But I just want to highlight that I think there's reason for hope. So if we go back to the example that I mentioned at the beginning, we wanted to think about given 11,000 learners' trajectories, could we learn a policy that increases student persistence? And we did a method that was basically sort of importance sampling based. And what we estimated is that our policy would be improve persistence by 30%. So that was our estimate. And so we wanted to double check that this estimate was, we expected this to be a good estimate. We expected it to be unbiased, but we wanted to verify this. And so we ran an experiment with 2,000 additional users online. And what we found is that we increased by about 30%, 32% in fact. And so I thought this was a really exciting result for two reasons. One is that we actually improve students' persistence by a large amount, which is exciting about whether machine learning can be helpful at identifying decision strategies that human experts can't always see in advance. And the second is that we could have a method that would predict the future before we did it. And so that would be sort of robust enough. Yeah?
What was the baseline policy? What were you comparing to?
Great question. So the baseline policy in this case was random. And random was actually better than the expert policy they were using before. So the data was gathered under a random policy, and so all of our performance was with respect to that. But there was another policy that was hand-designed before, and when we evaluated that offline, we expected it to be worse than random, which highlights why that in some of these cases it's really hard to write down a good policy. Like, I personally would not know, if someone placed a spaceship over here first or used a third instead of a half first, is that bad or good? What should I do next? And so in that case, I think it was really hard to write down a good decision policy. And when we did this verification experiment, the expert policy was worse than random.
So just kind of related to that, I was curious, what is the typical kind of horizon that we're talking about here? That, like, did you even have enough signal with the random policy?
Great question. So one of the reasons you might notice it with this a few years ago, and so this was one of our early works where we started to think about this. In this case, the horizon is pretty short. It's an online learning environment, so people normally play somewhere between 4 to 8 levels. It's a very short horizon. One of the reasons we started getting really interested in all of the sort of performance bounds is that the variance generally scales exponentially with the horizon, and so we needed different types of techniques. But in this case, where for better or worse, people were playing for quite short numbers of interactions, it was feasible to use sort of an importance sampling type technique to get these results. So I have some other stuff on the exploration side, but I think I'm going to just conclude with that, which is I think that it's really exciting to think about sort of what is the data we need to learn to make good decisions. In our exploration work, we've been thinking about lower bounds on that case. What's the minimum amount of data any agent, human, artificial, et cetera, would need in order to make good decisions? And I think now we're at the point where that problem is sort of solved for the tabular case. There's some really nice work from my colleagues at DeepMind that closed this for the regret bounds a couple years ago for episodic tabular reinforcement learning, and recently we closed it for the PAC setting. So I think in this case we now have a pretty good understanding of how much data we need and how to explore in order to get good data to make good decisions. And then I think also the second question of how do we leverage any old data that we have to try to make better decisions. That there's a lot of excitement also of how can we combine between these two. So both gather better data and then best use it in order to make good decisions. Thanks. Is there any questions? Yeah.
I was curious, so you were talking about your work with medical treatment rules and brought up semi-parametrics. I was wondering if you've done any looking into topic of adaptive designs for studies, and if that has some sort of...
Like optimal experimental design and things like that. I think it's a super interesting, so for any of you who didn't know, I was asked about, given sort of my mention of medical data, have we done any work on sort of optimal experimental design? I haven't. I think it's a super interesting, I feel like there's sort of optimal experimental design, there's dynamic treatment regimes, there's reinforcement learning, and none of those communities talk to each other. And so actually one of my colleagues, Noah Goodman, is going to run a seminar this fall on optimal experimental design. I'm super excited to attend. So if you have any pointers, I'd love those. I think the communities between epidemiology, biostatistics, and computer science are basically disjoint.
So you mentioned that one of the things you think people, maybe even especially outsiders, could work on are reducing some of the assumptions. Is there a variety that you brought up throughout, like realizability and maybe some of the conditions beyond the policies in order to be able to construct these covering numbers? Maybe do you want to say a few words about one of the other favorites or one of your favorites that you didn't talk about much?
Sure. I'm really interested in confounding. So the confounding question is that were there variables used to make decisions that we don't have access to or our algorithm doesn't have access to? So maybe when your doctor sees you, they notice that like one of your eyes is blue and one of your eyes is pink. And that means something really important of whether you get Tylenol or aspirin. But that's not written down in your electronic medical record system. So then when your policy is learning, the key challenge for why that's a problem, or at least the way I think of it, is that you don't have coverage. It may mean that like your policy is going to just prescribe things which you would never do, and so we're going to get wrong estimates. There's been some nice recent work from John Ducci's group and some of his colleagues thinking about how much confounding can affect your estimators. Can we scale down treatment effect estimation for a single decision if you have confounding? And we're trying to extend that to the sequential setting. And the reason I care about that a lot is that I think if we could do that, we could better unlock observational healthcare data. I think we're never going to know if there's confounding or not. Now, for better or worse, in America, we have fairly strong legal culture, which means that doctors have to have very good documentation about their decisions. So I also think that if we could do better NLP on those notes, you might imagine that we really would have all the features that doctors are using to make decisions, and then the confounding problem would be less strong. But I don't think we're there quite yet, so I think that's one of the areas that I think would be really great, because in practice, this has been a big problem for us for when we have existing data sets that we want to try to evaluate our methods on, because unless they're a randomized controlled trial, there might be confounding, and then you can't use it as ground truth to evaluate your methods. So if we have methods that are robust to that, then there's a lot of data sets we could start to use.
Perhaps a general question, how do you see the incorporation of game theory from the economic sciences into your field? There's a lot of talk about that.
Yeah, I think that's a really interesting question. Yeah, the question is like, how would we use game theory in terms of theories? I think there's a lot of interesting different directions for that, particularly for the safety and robustness side. I think it will be extremely interesting. Colleagues of mine that are doing work on autonomous cars, et cetera, I think, and also the multi-agent setting itself. Now, personally, I think it's also really interesting to think about the cooperative case, which we talk about a lot less, because you often have cases where, like, if the agent's interacting with a human, they're both jointly co-adapting in a cooperative way, and I think we don't pay enough attention to also what might happen in those scenarios. But I think from a robustness and reliability setting, there's a lot of opportunity for the game theory sets.
Okay, so let's thank Emma again.